As dealing with rational functions means looking at domains where we get everything except for some specific locations, it's natural to want to talk about what happens to the function, or at least get an idea of what should happen to the function as we approach those values. And to do that, we have a bit of a shorthand notation here that we call arrow notation, where if we write something like x with an arrow to a and a plus sign above it, what that says is we are approaching a from the right. We are letting our x value get closer and closer to a, but always be a little bit bigger. And then if we make that plus sign into a minus, we have x approaching a from the left, where that talks about looking at getting values closer and closer to a, but always smaller than a. And then we can do similar things with infinities, where if we have x approaches infinity, we are saying that we're letting x increase forever and ever, increase without bound, which we note with that x arrow and the infinity symbol. And then if we make that infinity symbol negative, that means we're approaching negative infinity, or we are decreasing without bound. Where we talk about this in terms of x because x is our general placeholder, but we can use that for anything we want there. We can talk about the function behavior as well with that sort of thing, as we're going to see here with a couple of quick examples. The first one we're going to look at is the most basic rational function that there is. F of x equals 1 over x. 1 over x is obviously, or at least I hope obviously, discontinuous at x equals 0, because you'd be taking 1 over 0, obviously a problem, like I said. And we might want to know, okay, it can't happen at 0, but what happens if we try and get close to 0? What happens with our function if we look at x values a little bit less than 0 and a little bit bigger than 0? So if we take x values like negative 1, negative 1/2, negative 1/10, negative 1/100th, negative 1/1000th, we'll see that our function f of x equals 1 over x has things like negative 1, negative 2, negative 10, negative 100, and negative 1000 as its values. And if we want to describe what that means, what we could say about that in terms of this arrow notation, we could say that as x approaches 0 from the left, f of x approaches negative infinity. That is, with the arrow going towards 0 with a minus, we get f going towards negative infinity, because as our inputs get smaller and stay negative, our outputs get larger while remaining negative. Meanwhile, from the right, we could do something very similar. Plug in things like 1/1000th, 1/100th, 1/10th, 1/2, and 1, get values like 1000, 100, 10, 2, and 1, where we would say there that as x approaches 0 from the right, as x gets small but stays positive, f of x gets very, very large. F goes towards infinity, where it's important to notice here that these sides, they don't agree, and neither can cross the y-axis. And this is something important that we'll talk about again in a little bit, but just for another example so we can see how this works a little bit more. If we take something like f of x equals 1 over x squared, and we talk about that same sort of notation, we have that as x approaches 0 from the left, because of the square, it's going to end up becoming positive, so it will approach infinity. Meanwhile, as x goes to 0 from the right, it's going to do essentially the same thing for essentially the same reason, except there won't be that squaring to deal with. It'll just do what it wants. And on the other hand, if we let x go to negative infinity, our function shrinks really quickly down towards 0, and the same thing happens if we let x go towards positive infinity, where those are the general ways we can describe these sorts of things using that notation. And just one other thing to note here, thinking in terms of both 1 over x and 1 over x squared, based on the symmetries we have, we could actually describe the former as being an odd function and the latter as being an even function. So things like even and odd in terms of the powers of x still works very similarly when those powers happen to be negative. But again, we can see here that there are some points that the function tries to get to but never quite reaches. Well, maybe it passes over them in certain situations, but it's always going to be trying to get back to where that was. And that is a very special behavior called an asymptote. And that's what we're going to finish most of this section talking about.